Okay. So here's problem 7-8. And we need to find the internal forces acting at point C, which is clearly identified here. I'll just put a big orange line there and say, hey, we're going to work the left or the right-hand side. It looks like we have a pin connection at A and a roller at B. Also, we mentioned before, all the loading is very symmetric, so there doesn't seem to be any advantage to one side or the other. But I'm going to choose the right-hand side just because there's a single reaction there. So I want to find my reactions at B. So the first thing we'll do is I'll draw a free body diagram of the whole structure. And on that, I'll put my reactions, AY, AX, and over here at B, there's just one BY. I have moments applied at the ends of these cantilevers of 900 pound-feet. And transfer those over. And then I'm going to have a concentrated equivalent force for my uniformly distributed load. What will be the value of that force?
6,000.
Yes, the area of the curve, so 500 pounds per foot times 12, that's 6,000 pounds. And it's located in the center, so that'll be 6 feet and 6 feet. I'll go ahead and put in the dimensions, and the overhangs are still 3 feet. So that should be a good free body diagram for this. So now I'm going to sum moments about point A. And why did I choose point A? Well, it eliminates two of my unknowns. Both AX and AY pass through A, create no moment, and I can solve for BY. One unknown, one equation. So let's do that. So we're going to sum moments. The first thing I'm going to do is I'll take care of my applied moments. So with right-hand rule as my sign convention, the one on the left is a positive moment, and the one on the right is a negative moment. So they seem to cancel. Now the 6,000 pounds creates a negative moment. So I have 6,000 pounds. And what's the moment arm about A? 6 feet. And I have BY creating positive moment with a moment arm of 12 feet. Looks like BY is going to be 3,000. You guys get that? Mm-hmm. So BY is 3,000 pounds. And now we're ready to solve the problem. So we'll come back over here and draw a free body diagram for this section CD. So let me come here and kind of redraw that. So I have my BY reaction, which I just solved for, which is acting up, of 3,000 pounds. I have my applied moment of 900 pound-feet. And I've got this distributed force and what's the concentrated equivalent for that? It'll be 500 pounds per foot times 6 feet. So this will be 3,000 pounds. And where is it located? Half the distance, so that would be 3 feet and 3 feet. Now I've got my internal forces. So There's my positive shear at C. There's my positive normal force at C. And there's my positive bending moment at C. Any questions about the free body? Now we just pile ahead with our equations. So again, it's usually best to sum the moments about the cut first. So in this case, I'll sum moments about C. Make sure it's at equilibrium. Again, the reason we do that is that the shear force and the normal force are passed through point C, so they create no moment. So since I'm using right-hand rule for my sign convention, even though this is a positive bending moment, when I sum moments with right-hand rule, this is a negative moment. My 3,000-pound force creates negative moment with a moment arm of 3 feet. I have another 3,000 pound, that's the reaction at B. That creates positive moment. And it has a moment arm of 6 feet. Then out here on the end I have this applied 900 pound-foot moment, and that in my sign convention is negative. So we should be able to put all that together and solve for the moment. This is 9,000 plus 18,000 is 9,000. It's like 800 and 8,100. You guys get that? Did I do that right? I did that right. That's right, isn't it? $8,100.
That's what I wrote.
And it should be positive. No, should be messed up. Hang on a second. Let's see.
That should be positive.
Yeah.
Oh, okay. Yeah. 8,100 pound feet. Positive. Okay. So what's next? Doesn't really matter. You can sum forces in either direction. I'll just sum forces vertical. So we'll sum forces in the y direction. Make sure everything's in equilibrium. So starting off, I have my shear force at C, which is up. My 3,000 pound concentrated equivalent force is down. My reaction force is up. Well, that's not hard to get. Looks like the shear is 0. And then if you sum forces in the x direction, make sure you're in equilibrium. What do you have? You just have minus the normal force. So the normal force is 0. That's not so bad. You guys probably hope for a question like that on the quiz, whether it's Friday or Monday. I'm not sure yet. But. So any questions about that? Okay. I'll stop.